Hi, this is Year 2 Pure, Chapter 9, Lesson 8, and today we're looking at implicit differentiation. And today we're going to be looking at how you can use implicit differentiation, not kind of how it comes about or anything like that. I just want to give you some ways that you can apply it really easily. So, implicit differentiation is used when you can't make x or y the subject of a particular expression or equation. So, for example, if you had x minus 2y equals 5, you could differentiate that. You can make either x or y the subject and you can differentiate from there. In this case, though, what you've got is something that's so complicated that making anything the subject of it is not going to be feasible. So we need to be able to differentiate this, but it's awkward. Now, whenever you can't make x or y the subject, you can differentiate using implicit differentiation. Now, when you've got terms that are just x terms, you can differentiate those as normal. That will be 9x squared, and this will be plus 2. Those differentiate nice and easy, really, really nice and easy. If you've got terms that are just y terms, differentiate just the y part, treat y as the variable, and then put dy by dx afterwards. So in this case, this differentiates 2y, and then put dy by dx. If you differentiate with respect to y, with respect to means with y being the variable. If you differentiate with y being the variable, you must put dy by dx at the end. Plus, we've got 5y differentiates to 5 dy by dx. And so what we end up with is 2y dy by dx plus 5 dy by dx plus 9x squared plus 2 is equal to, and this differentiates to 0. To get dy by dx, now what we'll do is quite a nice move, which is we're going to leave 9x squared plus 2 on the left hand side, but we're going to take all of this and put it onto the other side, so we'll end up with negative 2y minus 5 lots of dy by dx. You should be able to see what I've done there. I've taken away both of these things and I've factored out the dy by dx in one go. And then you'll end up with 9x squared plus 2 all over negative 2y minus 5 is equal to dy by dx. Okay, so we get some function. It's okay that that gradient function includes x's and y's. That's absolutely fine. It's not an issue at all. So the rule is, if you've got an x term, differentiate as usual. If you've got a constant term, differentiate as usual. If you've got a y term, differentiate and put dy by dx at the end. Okay? Now, in this question, you should be able to differentiate the first two terms, but the third one is going to give you a bit of a problem. So let's take a look at the first term. We've got an x term. This differentiates just as we would normally expect. This will be 10x. Plus, we're going to differentiate the y term, which is going to be 6y squared, but that was a y that we differentiated, so we'll put dy by dx. Plus, we're going to need to differentiate this. Now, whenever you have a term made of x and y, diff for both variables separately, then add. Okay, so what we're going to do is we're going to look at 2x cubed y to the power of 5, and we're going to differentiate that with respect to x. So we're going to treat x as the variable. Now, what I like to do when I'm making something the variable is I like to put everything else in front so that they look like constants to me. They're just numbers in this case. We're treating just x cubed as the variable, and we'll look at x cubed. So what I'll do is I'll have my constant and I'll have my differential of whatever's inside that bracket. Okay, and they will multiply together. So we're going to get 2y to the power of 5, 3x to the power of 2, which is going to be 6y to the 5x squared. And then we're going to differentiate with respect to y. Differentiating with respect to y will be 2x cubed is the constant, lots of y to the power of 5. So leave the constant there. We're going to differentiate, bring 5 down, take 1 off the 5, and you're going to end up with 10x cubed y to the power of 4, but we just differentiated with respect to y. What do we do when we differentiate with respect to y? If you differentiate with respect to y, put dy by dx. And so we'll have 10x plus 6y squared dy by dx plus 6y to the 5x squared plus 10x cubed y to the 4 dy by dx, which is equal to 0. Okay, and so our next step will be that we've got 10x plus 6y to the 5x squared is equal to, well, I'm going to take this over, so I'll turn them both negative, and I'm going to factor out the dy by dx in one go, so why not? So we'll have negative 6y squared minus 10x cubed y to the 4 dy by dx, and then in the end dy by dx will equal 10x plus 6y to the 5x squared over negative 6y squared minus 10x cubed y to the 4. And looking at that, you could divide through by 2, couldn't you? You can't divide through it by any parts of x or any parts of y, and so dividing through by the 2 will give you 5x plus 3y to the power of 5x squared over negative 3y squared minus 5x cubed y to the power of 4. There we go. Okay, so the rules are, when you've got a constant term, differentiate as normal. When you've got an x term, differentiate as normal. When you've got a y term, differentiate with respect to y, put dy by dx. When you've got a combination term, differentiate with respect to x, so that'll be treating y as the constant, add it to differentiating with respect to y, that's treating x as the constant, but you've got to remember to put your dy by dx on the end. Okay? So let's take a look at this question here. We've got, given that 4xy squared plus 2yx to the negative 1 plus 2x squared plus 3y squared equals 11, give dy by dx at the point 1, 1. So first off, we're going to have to find out what dy by dx is. Now, we've got a combination term here, so we're going to look at 4xy squared, and we're going to differentiate that with respect to x. Now, the way that I do that is I let the x have a bracket by itself, and that, when I differentiate, will be 4y squared. It will just be the constant because x differentiates to 1. And then we're going to differentiate with respect to y. So we'll have 4x lots of y squared, which will be 8xy dy by dx. Remember, whenever you differentiate with respect to y, put dy by dx on the end. Okay? And we've also got another combination term, which is generally whenever a combination term turns up, I tend to do quite a bit of working with it, and then after that it's just adding up basically. We've got 2yx to the negative 1. So we've got, with respect to x, you have 2y x to the negative 1, which will differentiate to negative 2yx to the power of negative 2. Lovely. And with respect to y, you have 2x to the negative 1 lots of y, which goes to just 2x to the negative 1 dy by dx. Okay, so what we're going to have in the end is going to be, for dy by dx, we're going to have this plus this plus this plus this plus the derivative of this plus the derivative of this is going to equal 0. So a lot going on here. So we're going to have 4y squared plus 8xy dy by dx minus 2yx to the negative 2 plus, that was minus by the way because there was a minus there, plus 2x to the negative 1 dy by dx plus, differentiate with respect to x, 4x, plus differentiate with respect to y, 6y dy by dx. Remember, whenever you differentiate with respect to y, you need dy by dx. That's going to equal 0. We're going to get all of our dy by dx terms on one side, everything else on the other. Now, here actually we could get all of the dy by dx terms onto one side, or all the other stuff onto the other side, and you'd actually get a form for dy by dx. That's absolutely fine. Once you've done this differentiation, because the differentiation has happened here, you can actually go to just subbing these things straight in, And often what that'll do is mean that you won't have to do so much rearrangement, and if you're not having to do so much rearrangement, it means that you'll resolve to numbers really, really quickly. And resolving to numbers really quickly, especially because it's the 0.11, which is quite easy to deal with, will make the next steps easier to deal with. It's quite a difficult rearrangement, and so because we've done the differentiation, you can make dy by dx the subject if you want to, and you'll get a full formula for it, but you don't necessarily need to. Once you've done that differentiation, you can just sub in 1, 1. So I'm going to sub in. So we'll get 4 plus 8 dy by dx minus 2 lots of 1 lots of 1 to the negative 2 is 2 plus 2 dy by dx plus 4 plus 6 dy by dx equals 0. 4 take away 2 is 2 plus 4 is 6. 8 plus 2 is 10 plus 6 is 16 dy by dx equals 0. 6 equals negative 16 dy by dx. 6 over negative 16 equals dy by dx. And so therefore dy by dx is equal to negative 3/8. Okay, quite a lot going on there. A really nice move here. That really nice move of not doing the rearrangement, not really worrying about it. If you did the rearrangement, you paused the video and you tried it out in advance, hopefully you still got negative 3/8. Right, moving on. In this question, what we've got is a combination term, which is e to the 3x natural log of y squared, awkward, plus 2x plus 3y equals 5. So quite a lot going on there. Now, to deal with this, the first thing I'm going to do before I do anything is I'm going to use a log rule here, just to tidy it up just a little bit. So I'm going to treat it as 2e to the 3x, the natural log of y. Okay, remember natural log of y squared is equal to 2 natural log of y. We should know that. And having natural log of y squared is something that we don't like to differentiate, but we do like to differentiate natural log of y. Okay, this whole thing's going to be 2 over y, isn't it? Plus 2x plus 3y is equal to 5, and so we're going to differentiate. So first off, we've got this combination term, so we've got 2e to the 3x natural log of y, and with respect to x, we're going to get, well, with respect to x, we're going to treat x as the subject, x as the variable, so we'll have 2 natural log of y, lots of e to the 3x, and we'll just differentiate inside this bracket, which is going to be 6 natural log of y, e to the 3x. Okay, not too bad. Differentiating this brings down the 3, which multiplies by the 2 to make the 6. Okay, and with respect to y, you'll have 2e to the 3x, lots of the natural log of y. When we differentiate that, we'll get 2e to the 3x. This differentiates to 1 over y. And remember, differentiate with respect to y, so we have dy by dx. Okay, so we're going to have this plus the derivative of this plus the derivative of that equals 0. Okay, but we're going to be trying to find out dy by dx of 1, 1 anyway, so we could rearrange, but we won't really need to. So let's take a look at what this goes to. So we'll have 6 natural log of y e to the 3x plus 2e to the 3x over y dy by dx plus the derivative of this, which is 2, plus the derivative of this, which is going to be 3 dy by dx, is going to equal 0. We can make dy by dx a subject, but if we've already done this is the differential, it just looks a bit terrible. We're going to just sub in 1, 1. So at 1, 1, we get 6 natural log of 1. Now the natural log of 1 is 0. So we're going to get 6 lots of 0, blah, blah, blah. Doesn't really matter. We'll get 0, basically. Plus 2e cubed over 1 dy by dx plus 2 plus 3 dy by dx will equal 0. So 2 will equal, I'm going to move all these things over, make them negative, so we'll get negative 2e cubed minus 3 dy by dx, and so dy by dx is going to equal 2 over negative 2e cubed minus 3. You might have made it look a little bit different. You might have had negative 2 over 2e cubed plus 3. Something like that is absolutely fine too. Alright, thanks very much for watching. Hopefully that helped. Good luck.